Hello students, welcome back to the moving charges magnetism lecture video 2. So in the lecture video 2 we are going to study the magnetic Lorentz force. Followed by that we are going to understand what is magnetic field intensity, and after that we are going to study Lorentz force, which involves both electric field and magnetic field concepts. And soon after that we are going to study velocity selector, which is dependent upon the Lorentz force concept. So let us start with our today's topics. We are going to study magnetic Lorentz force. Before I start this topic, let me tell you that we need to know 2 points. First point is, a stationary charge produces only electric field around it, and a moving charge produces both electric and magnetic field around it. So magnetic Lorentz force is the force experienced by a moving charge in the presence of external magnetic field. So to understand that, let us have a three-dimensional axis, and let us consider a charge moving with velocity v. Okay, so the charge is moving in this direction. So on that, let us have a magnetic field along x-axis. So there is a magnetic field along x-axis, and let the velocity vector v make an angle theta with the magnetic field. Then the force exerted by the magnetic field on the moving charge, I have taken the charge to be positive, you should note it. So the magnetic field exerts a force on the positive moving charge, that is given by Fb is equal to q v cross b. Since here velocity is a vector quantity, magnetic field is a vector quantity, we are taking cross product between them, and because of this cross product we get a magnetic force on the charge. This formula is given based on the experimental evidences. It doesn't have any derivation. So experimentally the things are matching to it, so it was taken. Right. Now here the magnitude of this force can be written by this formula, that is Fb is equal to qvb sine theta. So this is the magnitude of cross product. Simplifying the cross product, you get Vb sine theta, and in this case the direction is given by right hand screw rule or the cross product rule. We try to give the direction of force, and the force direction will be along y axis, as you can see in the image beside. Right, now let us try to find out how do we take the direction of the force, just by revising you the concept of the cross product. So let us try to understand what exactly is cross product. This is just a revising you. So here if you have a vector A and B, I have to do is take A crossed towards B. I have to curl A towards B, then I will get the A cross B along this direction. This A cross B is given by the right hand thumb. So this is the way we take cross product, and let us try to figure it out in our case of magnetic Lorentz force. So the direction of force is given by right hand screw rule. So I'm just going to place an image for you so that you can see it. So here is the velocity vector, and here we have magnetic field. I have to do is cross V towards B, then my thumb is pointing out in the direction of force. So it is V cross B. Remember, it is V cross B, and the angle should be here between V and B. So this can be simplified and written Fb is equal to qvb sine theta, and you get the magnitude of this force, and direction is given by right hand screw rule. Now here I have taken a positive charge. So because of the positive charge, I am getting the direction of force with the help of right hand rule. Assume that if I had a negative charge, what would happen? If I had negative charge, this q would be minus q. Because of that minus sign here, I would get the direction of FB exactly in the opposite side. That is, if the charge was negative, the force would have been in the downward direction. Remember that the force also depends upon the magnitude of charge, whether it is a positive charge or a negative charge, right? So here is the explanation for it. Proceeding further, we shall study magnetic Lorentz force and its cases. So let us find out when will be magnetic Lorentz force maximum. So magnetic Lorentz force can be maximum when theta is equal to 90 degree. So if theta is 90, here we shall have sine 90 as 1, and so I will get the value of magnetic Lorentz force equals to BQV. So this is the maximum value we can attain for magnetic Lorentz force. So magnetic Lorentz force minimum, when theta is 0, we get sine 0 is equal to 0, by which we can have magnetic Lorentz force as 0. And in case if there is no velocity for the charge, if charge is at rest, then magnetic Lorentz force will be 0. That means if the charge is at rest in the presence of magnetic field, it is not going to experience any force on it. So charge at rest does not experience any force in the presence of magnetic field. And also if the charge is 0, magnitude of charge is 0, that is 0 coulombs I can say. So if it is 0, then there will be no magnetic Lorentz force. This is in case of neutron. If you take a neutron and if you try to pass it through magnetic field, then it doesn't experience any magnetic Lorentz force on it, right? So proceeding further, in this explanation we talked about magnetic Lorentz force, but now we shall discuss what is this alphabet B. B is magnetic field intensity. So B is magnetic field intensity. So magnetic field intensity can be taken out from the concept of magnetic Lorentz force. We already know the formula for magnetic Lorentz force. I'll just alter the formula in such a way I get the value of B. Now B is equal to FB divided by QV sine theta. In this formula, if I substitute Q is equal to 1 coulomb, velocity is equal to 1 meter per second, and theta is equal to 90, then I'll have the denominator as 1. And if I have denominator as 1, then I'll get the equation to be B is equal to FB. That is, magnetic field intensity will be equal to magnetic Lorentz force in terms of magnitude. So then I shall be easily be able to define what is magnetic field intensity. So definition goes like this: magnetic field intensity at a point is defined as the force acting on a unit positive charge, that is acting on a unit positive charge, moving with unit velocity, perpendicular to the direction of magnetic field, right? So here the SI unit of magnetic field intensity is Tesla. So Tesla is the name of a scientist, Nikola Tesla. So in his remembrance we have put the name Tesla as a unit of magnetic field intensity. Moving ahead, we shall try to define what is 1 Tesla. So to define 1 Tesla, once again I'll try to take magnetic Lorentz force equation and I'll try to make B is equal to 1 by all the other values. So here let me substitute Q is equal to 1 coulomb, velocity equals to 1 meter per second, theta is equal to 90 to make sine theta is equal to 1, and I'll put Fp is equal to 1 Newton, that is magnetic Lorentz force equals to 1 Newton. If I substitute all these values, then I'll get the value of B is equal to 1, and that should be in terms of Tesla. So this comes out to be 1 Tesla. The magnetic field at a point is said to be 1 Tesla if a positive charge of 1 coulomb, moving at right angles to the magnetic field, or else you can say moving perpendicular to the magnetic field with a velocity of 1 meter per second, experiences a force of 1 Newton. Did you understand this? This would be the definition of 1 Tesla. Right. So here we shall note that Tesla is a huge term or a huge number to measure the magnetic field. So a non-SI unit which is smaller in term is taken most of the time. So that is Gauss. So 1 Gauss will be equal to 10 raised to minus 4 Tesla. So it is important from the point of view of numericals. And Earth's magnetic field is about 3.6 into 10 raised to minus 5 Tesla. So in terms of Gauss, it comes out to be 0.36 Gauss. So Gauss is also sometimes an important term in trying to give the magnetic field intensity at a point. Right. Moving ahead, let us now try to study what is Lorentz force. Lorentz force is the force experienced by a charged particle moving in the presence of both electric as well as magnetic field. This force is given by a formula. F is equal to force because of electric field plus force because of magnetic field. It is vector sum of force exerted by the both fields. Now here, to get the value of electric force, I'll use this formula here, which is shown here, that is E is equal to F by Q, that is electric field intensity formula, which you have studied in your previous chapters. So by this I can write F should be equal to QE, right? So I can represent F force because of electric field will be equal to QE, and in case of magnetic field, that is I'll try to take the value from magnetic Lorentz force, then I shall be able to write here this as QV cross B. Now putting them together, I would get an equation for Lorentz force as QE plus QV cross B. Now since the charge is same, which is experiencing both the fields, so I can take it common, and I shall write it as F equals to Q into E plus V cross B. So this formula gives us the value of Lorentz force. So this is the Lorentz force equation. Moving ahead, let us try to study velocity selector. Velocity selector is an arrangement of uniform electric field and magnetic field perpendicular to each other. So in this region, the electric field and magnetic field which are perpendicular will try to allow charged particles of only specific velocity to pass through this region. So such an arrangement we call it to be velocity selector. So this device or this method will be helpful in picking up the charged particle of only one specific velocity. So to understand that, we shall try to explain it using a diagram which would be following now. So let us try to take a coordinate axis in which I will try to first of all study the electric field effect on a charge, and followed by that I will try to study magnetic field effect on a charge, and finally I am going to combine both of them and try to make you understand what exactly is velocity selector. So let us try to take a charged particle which is placed at the origin, and this charged particle is a positively charged particle, and we shall try to take a electric field, uniform electric field along y-axis. Now you know that the force on the charged particle will be along y-axis. It would be written like this: Fe is equal to QE. So I am taking the magnitude of this. So magnitude would be QE and direction is along y-axis, positive y-axis. Now further, if I try to take the same thing for magnetic field, so I'll be able to write it like this by taking a positive charge at the origin, and here I'll try to keep the charge in motion with a notation of saying that it is having a velocity along the x-axis, and soon after that I shall be taking magnetic field along z-axis. So magnetic field is along z-axis, velocity is along x-axis. Now the force on this one can be given by right hand rule, and that would be appearing in the downward direction, that is along negative y-axis. So the value of that I can write it to be QVB, and here sine theta, that is angle, comes out to be 90 degree. So sine 90 is 1, so I get the force value of FB, that is magnetic Lorentz force on the charge, will come out to be QVB. Now the angle, you can see it here, it is here between V and B, it is 90 degree, that is x-axis, and z-axis it should be 90 degree, right? So I have got this value. Now my interest would be trying to take or merge these two, that is trying to take in such a way that electric field becomes perpendicular to magnetic field. Now I would merge both of them in this manner and try to get the things right. So here I have an electric field along y-axis and magnetic field along z-axis, and they both come out to be perpendicular. Further, my interest would be trying to take the forces to be in exactly equal values. That is, I mean to say that I want the force because of electric field to be equal to force because of magnetic field. Once if both of them are equal, I can make the net force on the charged particle to be 0. If the force on the charged particle is 0, then the charged particle moves along the same direction without deviation if these two are equal in magnitude. So if they are equal in magnitude, then I'll be able to write Fe is equal to Fb, and further I can substitute their values. Fe will be equal to Qe is equal to QVB, the value of magnetic Lorentz force here, and the force on the charge in the presence of electric field. Further, I can cancel the Q and Q since I have taken the forces acting on the same charge. Okay, these two forces are acting on the same charge, so here I have taken the same Q, so I can cancel it off easily. So I get E is equal to VB, and further if I write down, I get to know that the ratio of electric field to magnetic field will be equal to velocity. So the velocity will be selected based on the value of electric field and magnetic field. This is a technique of velocity selector. This is the way we can select a charged particle to come out of a region having a specific velocity. Now if you still didn't understand, we can try to take a significance of it, that is how does it exactly work, to show you what happens inside this region when there is many number of charges, like some charges which are trying to move with different velocities. Okay, so let us try to understand what exactly happens. So here let us try to take a coordinate axis. In this, let us have a magnetic field along z direction and electric field along y direction, right? And I am taking few of the charges, and here I have not mentioned any value for the charge. Charge can be any one, right? So almost all of them might be positive, and maybe different in magnitude. You can try to take 1 coulomb, 2 coulomb, 3 coulomb, doesn't matter, whatever you take, right? But velocities are different. So here our total concept is based on selecting the charged particle based on their velocities, not based on their charges. Clear? I am selecting a charged particle based on its velocity. Now remember, choosing charged particle based on the velocity means velocity can lead to kinetic energy. I hope you people know that velocity is used to explain kinetic energy. That is, V can be used in the formula of kinetic energy. That is, kinetic energy is equal to half mv square. If I try to pick a velocity, right, I pick a certain velocity, that means I am trying to pick a charged particle with certain kinetic energy. Understanding this? So that's why we are trying to use this concept of velocity selector. So here, if I try to allow these charged particle to move in this perpendicular electric and magnetic field arrangement, so what happens? So there will be two forces which will try to act on these with a different way, okay, with different magnitudes. So what happens? Let us see. Once I try to allow all the three of them, so they are going to go in these directions. So only one among them was able to go undeviated, the other two got deviated. Let us try to find out what exactly happened. So here the one which was undeviated was with value V, and the other two which got deviated were having V1 and V2. Here I have mentioned that V1 is very lesser than V and V2 is much greater than V. So why was V allowed? V is allowed, that is, the charged particle with velocity V is allowed. Reason for that is this one. So this velocity matches to the value of E by B. So that's why this charged particle got a green signal and it was trying to move in same direction. Further, what about the other two? In the other two cases, what happens? These two values are not equal to the ratio of electric field by magnetic field. So if this ratio is not matching to the velocities, then those particles will get deviated. So slower charged particle will go along the electric field direction. The faster particles will be affected by the magnetic Lorentz force. That's why they bend it towards this direction. And the one which is matching to the ratio of E by B will go undeviatedly. And then we can pick the particle of certain velocity itself. And certain velocity means a certain specific kinetic energy, and these particles will further be used to hit the target and to study their structures. This was all about what I had to teach about velocity selector. So thank you students. We'll meet you in the next video lecture.